We're going to start off this video by looking at something called a Lewis structure or a Lewis diagram. And they are diagrams that show the number of valence electrons that an atom actually has. So recall from the Bohr-Rutherford diagrams that we would have drawn in a previous lesson that a shortcut for this is the group number that the element in is going to tell you how many valence electrons that atom has. So some examples. If we're looking at lithium that is in group 1, it has one valence electron. You can draw it as a dot, an X, a heart, a triangle, whatever you want. I'm going to draw this one as a dot. The next one in group 2 we'll do is calcium, and so it's group 2, so it has two valence electrons, so I'm going to draw them top bottom. Electrons are negatively charged, they're repelling each other, so we're going to draw them as far away as we can. Aluminum's in group 3. It has three valence electrons. Notice they are again not together. Carbon's in group 4. So it will have four valence electrons. Now, something a little unusual is going to happen here when we get to group 5, which is called nitrogen, or nitrogen's an example. We're going to put our 4 in, and then when we go to do our fifth one, we're going to pair it up. So we have something here that's called a lone pair. Lone pairs are very stable. In fact, this is sort of the goal of all atoms, is they want to have a bunch of lone pairs. You'll notice that all the ones we did previous to this, there were no lone pairs, which means those ones aren't really happy with themselves. And as well, too, this one has 3 spots where lone pairs don't exist, so those spots are not exactly happy either. Now, as we move on to group 6, we look at sulfur, and when we put this one together, you'll notice that we have 2 lone pairs, and iodine is in group 7. And when you put all these ones around, you'll notice that we have 3 lone pairs. And when we get to group 8, argon's an example, and it has a full 8 valence electrons. So this is the goal. So this argon here is very stable. In fact, out of the 8 we just looked at, this is the only one that's going to be stable, and it's just going to stay as is. So we're going to have to do some work with the other atoms here that we've looked at. So what's going to guide us is something called the octet rule. So when we're looking at stability of ions, the octet rule states that either atoms are only stable, whether they have 0 valence electrons or 8 valence electrons. And as we just discussed, that out of the ones we just drew, only that very last one, the argon, was the only one that was actually happy and stable. And so the rest of them are going to have to do something to become stable. And what that thing is they're either going to have to gain electrons from somewhere or lose electrons to become stable. So let's start with some metals. And let's pick one from group 1. Let's go with lithium. So it has, it's in group 1, so it has 1 valence electron. So we know that this is not stable right now. It's not following the octet rule. So how are we going to get this down to 8? Or up down to 0 or up to 8. Well, the move's going to be either this one's going to lose 1 or gain 7, and we're always going to go with the lowest number. So lithium is going to lose 1 valence electron. So here's what we're going to do. We're going to take that electron away. It's now free, flying around somewhere, but lithium has lost something that's negative. So its overall charge has gone from being neutral, it's lost something that's negative, and that means there are more positives that remain in the atom. So it has a charge of positive 1. And then we'll also write that 1 electron. So that one is in fact that one. So what we've discovered is lithium's stable charge is +1. In fact, that applies to all the group 1 elements. All of their stable charges are going to be +1. When we get to group 2, we already looked at calcium. It's got 2 valence electrons. So what calcium's going to do is lose 2, gain 6. Well, it's going to lose 2. So if it loses 2 negatives, it's going to have an overall charge of +2. And then there are those 2 electrons. And group 3 is the last one we'll look at here, aluminum. And so you might have already jumped to the conclusion that this aluminum is going to kick those 3 off. It's going to have a overall charge of +3. And we've got our 3 electrons. So we've actually made a discovery here, because remember, these are all metals. So we have discovered that metals will lose valence electrons to become positive, stable ions. And the fancy name for a stable positive ion is a cation. Looks like a big T, looks like a plus sign. That's how I remember cations are positive. So that's just half the story. Our periodic table also has a bunch of nonmetals on it. So let's look at those two. Actually, before we get to that, I should mention that you can actually find these stable charges on the periodic table. So there was lithium, it has +1. There's sodium, it has a +1. Potassium has +1. Beryllium +2. Aluminum +3. These ones in the middle here, they have a couple of positive charges to them. We'll explain those in a future lesson. So you can see that our metals, they all have positive charges to them. And if you want to know what it is, you just look it up on the periodic table. So now on to the nonmetals here. Now we're going to ignore group 8 because those ones are stable. They don't want to gain or lose. They're already happy. So we'll look at something from group 7, which is chlorine. And this one is at 7. So to get up to 8, it just wants to gain 1 electron from somewhere. So we're going to draw this one. Well, we'll do something a little different here. We'll draw our chlorine in. And now we're going to use a different symbol to represent this 1 electron here. And now since we've added an electron to this chlorine, we have an overall charge of -1. So that is chlorine's stable charge. It is -1. Group 6, like sulfur, it has 6 valence electrons. So we kind of have 2 spots to put things in, right there and there. So we're going to add 2 electrons. And when we do that, we'll have an overall charge of -2. And when we get to group 5, we've got our nitrogen. So now we have 3 spots to put some electrons. So we'll add 3 electrons in. And there we go. And if we've added in 3 negatives, that means we have an overall charge of -3. And we have made a discovery again. We have discovered that nonmetals are going to gain valence electrons to become stable negative ions or anions. So if you think about it, metals are losing, nonmetals are gaining, so they're going to go together and make a nice match. And again, on our periodic table here, you can see that for our nonmetals, we've got fluorine at -1, chlorine at -1, bromine, iodine. There's oxygen, there's sulfur, selenium, nitrogen, phosphorus, and sometimes carbon. These are really the only nonmetals we're going to use in our early examples here. So let's talk about some ionic compounds. What is an ionic compound? Well, it's a compound that contains an ionic bond. Well, it doesn't really tell us anything. We need to look a little bit further here to figure out what an ionic bond is. And, well, an ionic bond is created when electrons are lost from a metal and gained by the nonmetal. That's what we just kind of mentioned as well in the last slide there. So another way of saying this, and this is really more the official way, I would say, is ionic compounds are made of metals and nonmetals. And even another way of saying this is that we've discovered that metals turn into cations and nonmetals turn into anions. So another way would be to say they're made of cations and anions. So let's go through some examples here. So what happens when we put sodium and chlorine together? So sodium is a group 1, it has a 1 valence electron. And chlorine is a group 7, it has 7 valence electrons. So they make a good match because sodium wants to lose that 1 and chlorine wants to gain 1. So what we'll do is we'll draw sodium without any valence electrons because it's lost its 1. And then we've drawn chlorine where it has gained 1. And we've made our discovery that every time you put sodium and chlorine together, you are going to end up with 1 of each. And this happens to be our formula when you put sodium and chlorine together. You get sodium chloride. And that's the naming rules here as well. So firstly, you'll name the metal. The metal comes first. It's sodium, so you call it sodium. And then you name the nonmetal with an "ide" ending. So chlorine becomes chloride, sodium chloride. Let's try another one here, magnesium and fluorine. So magnesium is in group 2, and fluorine is in group 7. So this starts well. We can fill fluorine up, but the fact is that magnesium is still unhappy. It still has an extra valence electron. So we'll add another fluorine. And we can put that valence electron right in that spot. So if you draw this one out, it looks a little like that. We'll make it symmetrical. We'll put magnesium in the middle. And there is the shape of our molecule. And our formula of the molecule is we've got 1 magnesium and then 2 fluorines. So MgF2. And we go to name this one. Follows the same convention, magnesium fluoride. Last one here, aluminum and sulfur. Aluminum has 6, aluminum has 3 and sulfur has 6. So this starts well. We can put that one there and that one there per se. And then we'll add in another sulfur, and we can take aluminum's electron and put it there. But now we need another aluminum because sulfur's not quite filled up. And then we're almost there as we take that last one and put it there. And now we have done it. And this is starting to get a little out of control here. So our molecule looks a little something like that. Our formula is Al2S3, and that one is aluminum sulfide. This method it started nice. It's starting to get a little complicated. So we do have an easier way of doing this, and it goes back to those stable charges on the periodic table earlier. So the crossover method. Let's just do an example and we'll talk about how this works. So the last one we did was between aluminum and sulfur. So the first thing you do is you go to your periodic table and you look up the stable charge of aluminum, which happens to be +3. Then you look up the stable charge of sulfur, which happens to be -2. Now, so how do we figure out how many of each element there is in our compound? So we're going to write aluminum first, and then what we do is we look at the number, just the number, we don't care about the charge, with the other atom, and it's going to come down and become our subscript here, Al2. And then to figure out how many sulfurs you've got, you just look at the number there, and it comes down, and it tells you you have 3 sulfurs. Aluminum sulfide. Now, we did just draw this one. If we flash back to that slide and remember this formula, let's confirm if we did it right. Sure did. There it is, the same formula. Maybe we should double check our other 2 examples as well. So this one was the magnesium and the fluorine. You look up magnesium stable charge, it's +2. Look up fluorine stable charge, it's -1. So how many magnesiums are we going to get? Well, we're going to get 1, but we're not going to write the subscript 1. By writing Mg, we know we have 1 of those ones. How many fluorines will we then get? The 2 comes down, we get 2. We get magnesium fluoride. Let's double check. MgF2. MgF2. That's what we got earlier when we drew it here. And lastly, sodium and chlorine. They each have charges of 1. So when you cross them over, they each get 1. Sodium chloride, NaCl. And that's exactly what we found here for NaCl. So a couple more examples to finish this off here. Magnesium oxide. So you need to look up magnesium's charge, and it has a stable charge of +2, and you look up oxygen's stable charge of -2. And your first thought might be, our formula here is going to be Mg2O2. Well, that's not really the case, because magnesium wants to lose 2 valence electrons, oxygen wants to gain 2 valence electrons. So really, we just need 1 of each. MgO. So picture this as really kind of being reduced. It's like a fraction that got reduced to lowest terms, I suppose. But this also applies when you get the charges both being 3. Again, aluminum loses 3, phosphorus gains 3, so you only need 1 of each atom. The bottom line here is when your charges are the same number, whether they're 4s, 3s, or 2s, or 1s, you end up with 1 of each element in our compound. Magnesium carbide, Mg+2 and C-4. If you look up carbon, it's got a few positive charges in that box, but we're interested in its 1 negative charge because anions, the nonmetals, are always negative. And when you cross this one over, you get Mg4C2. Now, this one's not quite done. This is one of the few examples for ionic where we actually need to kind of turn it into lowest terms. We need to divide each of them by 2. And we get MgC2. And that ends up being our formula. Like I said, this won't happen very often, but just keep your eyes out for it.